Good afternoon, everybody. Welcome to another round of VTSS. And today we're very happy to have Christian Brownlees with us and Jonas, who's going to be discussing the paper. Christian, you have 1 hour. The floor is yours.
Perfect. So first of all, thank you so much for having me in the seminar series, and also thanks so much for joining. Today, I'm going to talk about performance of empirical risk minimization from principal component regression, which is joint research with Stefan Gudmundsson, who's prof at Aarhus, and Yaping Wang, who's my PhD student here at UPF. So, well, let's get started. So I just wanted to say, we're currently finishing the first draft of the paper. In particular, right now, the paper is in Stefan's hand, who should be joining the seminar in a little bit. So if you have any complaints, Stefan is the person to ask, because he should have finished his job by now. So let's get started. Let's talk about the topic of this paper. So this paper is about learning theory. What is learning theory? Learning theory is essentially the theoretical backbone of machine learning. And a key principle, one of the first principles that was introduced in the learning theory literature to, we would say as econometrician, estimate models, is empirical risk minimization. And so there's a very big literature in the machine learning theoretical literature that establishing the properties of this estimation approach. What is empirical risk minimization? Well, we may not be familiar with this terminology in econometrics, but empirical risk minimization is a very simple principle. Imagine that you want to forecast some random variable yt, and that you have available for forecasting some class of decision rules or some class of forecasting rules denoted by f theta t, and that this class of forecasting rules is indexed by theta. Well, the empirical risk minimization principle says simply pick the forecasting rule that minimizes the empirical loss when you predict yt for prediction. Okay, so pick among all the possible f thetas, the one that gives you the smaller risk in sample, essentially. So as a principle, this is kind of makes a lot of sense. It's just kind of like English squares in a way. Okay. Now, a key feature of the contributions in machine learning theory, that use empirical risk minimization, is that a key aspect of the theory that they developed is that typically in this literature, it is assumed that the relationship between yt and f theta t is not specified. So in a way, learning theory attempts to be non-parametric. You have a class of procedure to forecast, you have data, you know nothing about the relationship between the data and the class of forecast, and you want to establish performance guarantees on how well your forecasting algorithm is going to perform. In particular, one of the key objects of interest in learning theory is the following. So people in learning theory are interested in establishing non-asymptotic bounds on the predictive performance of the forecasting rule that is chosen by empirical risk minimization. Okay, so I'll get back to what this means a few times during the presentation, but I'll emphasize this a few times. Let me start emphasizing it from now. So essentially what people care a lot in this literature is that they would like to get a bound on what is your forecasting performance relative to the best performance that you can possibly achieve. And you would like this bound not to be asymptotic, but be something that holds in finite samples. Okay, so, we can have discussions about whether we like this performance measure or not. And, when I present this paper or papers in this area, there was a bit of debate over the whether we like this performance measure or not, and that is fair. But let me say that, this is what people care in this literature. Okay, so, in this sequence of papers that I'm writing on empirical risk minimization, I'm trying to do things the way a statistical learning theory guy would like to do. Now, if you look at contributions in the learning theory literature, I have to say that this literature is in a way a little bit, disappointing is a bit of a strong word, but let me use disappointing. It's a bit disappointing for a econometrics time series guy, because essentially the bulk of the contributions in this literature focus on the analysis of IID bounded data. And the results that books or papers have for ID-bounded data really do not generalize to the time series setting, in the sense that, if you think, for instance, of non-parametric estimators, it is often the case that proof in the ID case and the dependent data case are kind of similar, but you have to use appropriate law of large numbers, say, for dependent data. Well, when it comes to learning theory, it turns out that sometimes you actually have to resort to fairly different proof strategies. And so what I'm trying to do, and I've been doing this for a few papers now together with past and former PhD students, is that we're trying to establish results for empirical risk minimization when the data is dependent and unbounded. We have a few papers on this topic. I have a paper on large dimensional linear regression with Stefan that we just got on ET. And then we have a paper for Armagh-Garch type prediction rules and for caviar type prediction rules. And this is joint research with Jordi, who's now a professor in Sarri, with Valentina Corradi. And in this paper, what we're trying to do is that we're trying to build in the sequence of papers, and we're analyzing a new estimation strategy. And this new estimation strategy is principal component regression. The main contribution of the paper is essentially to establish non-asymptotic prediction guarantees, an oracle inequality for principal component regression. Now, let me give you a few highlights about the type of analysis that we're going to carry out. Now, first of all, needless to say that in econometrics and the time series literature, principal component regression / factor models have a huge literature, hundreds of contributions written by experienced smart guy. Principal component regression is essentially something that we've been doing before big data was cool in econometrics. So there's a lot of stuff out there. So what is different between this paper and the type of results that are out there already? So first of all, in this paper, we are going to study the gap between the predictive performance of principal component regression, so how well your forecast based on principal component regression is under the square loss, with respect to the best linear predictor that you can construct using the set of predictors that you use to do principal components. Okay, so the performance measure that I'm interested in is the one that I have in the first display of this slide. This is defined in a bit of loose terms. I'll give you the better definition in what comes next, but this is just to fix ideas. Second aspect of the analysis, which maybe is of interest, is the following. We do not assume that the data is generated by a factor model. So in particular, we do not assume that, we don't make any specific assumptions between the relationship between YT and XT. So in a way, we just treat principal component regression as a regularized regression technique. And we're interested, as if it could have been Lasso, but instead of using Lasso for some problem, you may want to use principal component regressions. And so essentially, we're just treating this tool as regularized regression technique. To be clear, lots of the assumptions that we will have are very similar to the assumptions that people do in the factor model literature. So it's not like we're kind of reinventing the wheel, we're kind of carrying out our analysis using fairly standard assumption and proof strategies, as we shall see more detail later. But in a way, if you want to interpret principal component regression as something that you may want to do if you have a data generated by a factor model, you can. But you don't have to, and that's somehow the viewpoint that we emphasize in this paper. A third aspect of the analysis is that a key aspect of our procedure is that we establish performance guarantees under the assumptions that the largest eigenvalues of the population covariance matrix of the predictors diverge as a function of the dimension of the covariance matrix, which is standard in factor models. Since we don't assume that we have an underlying factor model structure, we call the largest eigenvalues that diverge signals. And in the theory, we allow for both strong and weak signals. Strong signals is when the largest eigenvalues of the population covariance matrix diverge at the rate p. So this would be precisely the case of the classic factor model with pervasive factors. But we also allow for weak factors, and in particular, we allow for the rate of divergence of the largest eigenvalue of the covariance matrix to diverge at rate p power alpha, where alpha is in between 1/2 and 1. Okay, we cannot allow right now for alpha between 0 and 1/2, and as of now, I believe that we cannot, and I'll show you why. Well, I'll give you some insights into why, but we're still kind of thinking about it. So the weakest signal we can handle is the eigenvalues diverging as the square root of p plus a little bit, plus epsilon. A bit of related literature. First of all, principal component regression has been around since the 50s. So it's a method that people have been using in statistics for a very long time. Humongous list of contributions on this topic in the econometrics literature. These are just a few. In this paper, really at the end of the day, we rely on the kind of proof strategies and the formalization carried out in a number of papers by Bai and Eng and Fao, Liao, and Mincheva in 2 different sets of papers. Really, Fan and co-authors build up on top of Bai. So really, Bai and Eng is, at the end of the day, where it also started. Most of the papers out there typically kind of focus on the estimation of the factors. There are fewer papers that focus on kind of predictive properties. An important paper that I would like to mention is recent research by Fan, Medeiros, and Massini, who just got accepted on the Annals of Statistics. That it's a paper similar to ours in the sense that they also study performance guarantees, but they have a kind of a more general framework in which you kind of see a little bit less what's going on. We have a more specialized framework, less general than theirs, but we can have a better taste of the various pieces that contribute to contain your estimation risk when you carry out principal component regression. So that's it. Let me show a little bit the basic framework and let me introduce the main result. So what is the setting? Assume that we have some sequence of stationary vectors. This sequence of stationary vectors is partitioned into YT, which is the target series that you want to predict, and some vector xt, which is p-dimensional, which is the set of predictors that you would like to predict YT with. Problem is that p is large, and so doing least squares here may not be a smart thing to do. So what we do here instead is that we rely on principal component regression. I'll have 2 slides about principal component regression, but here we're really doing kind of vanilla principal component regression. So I like to think that everyone is familiar with it, but I'll talk a little bit about it just to introduce notation in any case. PCR is essentially a regression procedure based on 2 steps. First step, you compute the principal components. We compute k of them, and I'm going to denote the principal components by pt hat. And then in the second step, you run a regression on YT on pt hat. And then once you get your estimator, you use your estimator for forecasting future observation. A few more details. So first step of principal component regression, in a way, consists in computing the matrix of principal components. Essentially, what these are, you can think of this as kind of a low-dimensional, low-rank approximation of your data matrix. It is the solution of this constraint least square optimization problem, and as it is well known, what's great about principal components is that they're available in closed form, and they're easy to compute once you can do the spectral decomposition of the sample covariance matrix. And in the last display, I gave you the formula of the sample principal components. So p hat here will always denote sample principal components. This is the first step. So you synthesize your data by just looking at the first k principal components. And then in the second step of your principal component regression, you just run a least square regression. And we all know how the least square estimator looks like. What's nice about principal component regression is that because of the normalization assumption that we're making when we're computing principal components, the least square estimator has an even easier formulation than it typically has, which is simply the covariance essentially between the sample principal components and the data. So it is trivial to compute. Of course, we all know there's a procedure that is very stable, works well with very large data sets, and we know that it empirically works pretty well. Now, first thing that it's important to address is that it is not clear at all that principal component regression is empirical risk minimization. So let me explain this properly. What do I mean? Empirical risk minimization means you have a class of prediction rules, pick the one that minimizes the empirical risk. But since PCR is a 2-step procedure, it's not really clear whether you're actually minimizing something. Well, it turns out that you are indeed minimizing something when you're doing PCR. More precisely, it turns out that you can interpret principal component regression as a special case of a constraint least square estimation problem. In particular, it is straightforward to verify the following. So say you're interested in computing the least square estimator of the regression y on x. So you simply predict y using all the available predictors, but you want to impose the following constraint. You want your least square coefficient vector to be orthogonal to the matrix of sample, I call them residual eigenvectors, that is, the eigenvector associated with the eigenvalues that go from k plus 1 to p. Okay, so the eigenvector associated with the signals that we're kind of thinking implicitly that don't really matter. Then it turns out that it is straightforward to establish that computing the least square estimator subject to this constraint is essentially principal component regression. That is, to be more precise, it turns out that there's a one-to-one mapping between the least square estimator associated with this constraint regression and the least square estimator obtained by principal component regression. The mapping is the one expressed in the penultimate display of this slide. And in particular, if you want to forecast, that's what we care about here, forecasting using the least square PCR estimator or forecasting using principal component regression gives you the exact same forecast. So, these are two alternative ways of looking at principal component regression. And for our purposes in the paper, this is kind of the representation that we care about, because as I said, we're not going to make kind of assumptions that the data is generated by a factor model. We just want to treat principal component regression as a regularized estimation procedure. So this is how we make the connection. Cool. So principal component regression, we all know and love. Issue is, what properties does this procedure have? So that's, in a way, kind of the core of learning theory in a way, in the sense that it is often the case that when you read machine learning textbooks, sure, sometimes they rely on linear methods, but ultimately we're not really doing stuff that is very different from what we're doing already. But what, in a way, it's a little bit more different is the way they kind of study, is the kind of properties that they care about establishing. So in a way, here is where things get a little bit more interesting and more new. So in this work, we're interested in establishing an oracle inequality for principal component regression. So what do I mean by oracle inequality? I want to establish a bound that bounds the gap between the performance, the out-of-sample performance of principal component regression and some appropriate benchmark. Okay. Now, let me talk about the benchmark first because it's easier. In this paper, we choose as the benchmark the risk of the best linear predictor. Okay, so we have a bunch of predictors in XT. We don't want to make assumptions of how the data is generated. Well, under minimal assumptions, you can still define the best linear predictor, so the best linear forecast you could construct using your vector of forecasts. So we're kind of interested in measuring the performance of PCR relative to this benchmark, which is here. Okay. Let me also point out that, here in this notation, I'm kind of implicitly assuming that the best linear predictor is unique because I'm having a theta star. We're kind of making sure everything goes through, but actually the analysis goes through even if the best linear predictor is unique, but even if theta star is not unique. Okay, so we don't require, for instance, the covariance matrix of the x's to be invertible. Okay, it can be allowed to be singular. So this is the benchmark. What about the accuracy measure? So the accuracy measure that we're using is this conditional expectation over here. So let me explain this a little bit. We're looking at the expected square loss between the target time series that we care about predicting and the forecast constructed from PCR. Now, here is something a little bit delicate that if you want, we can talk a little bit more about. What I'm assuming here is that I have some in-sample training data that it's called denoted by D. I use my in-sample training data to compute PCR and to compute essentially my PCR estimator. And then I have a validation observation, and I use the PCR that I computed in sample to forecast out of sample. My performance measure is the conditional expectation out of sample of my PCR estimator computed in sample. Okay, so it's a conditional expectation of how you're going to perform out of sample given the data that you have in sample. So far, so good. Important aspect that simplifies the analysis a lot is that I'm assuming that the validation observation is drawn independently of the training data D. Okay? Now, this requires a bit of explaining. Okay, so typically in learning theory, they have exact same assumption. Since in learning theory, we assume the data to be IID, it's absolutely not problematic. Okay? Clearly, in time series, assuming that the out-of-sample observation is independent of the sample observation, it's something that we don't like to assume. Now, we can talk more about this, but let me kind of give you my summary answer, and I hope this satisfies you. So it turns out that you can do the same analysis by allowing for dependence between the out-of-sample data and the in-sample data. You can. But it turns out that the type of analysis that you have to do when you allow for this dependence is the same that you would have in this case, but you have to introduce much more notation. So in other papers that I've done on the topic, we have considered out-of-sample criteria that are more appealing from a time series perspective, but it doesn't really change the nature of the analysis, and it just makes the presentation of the framework a little bit more complicated just because I have to introduce more notation. So I'm avoiding it in this paper, but if it's something that bothers you particularly, we can talk about it. But then, the long story short is that you can handle alternative performance criteria. In particular, you can allow for dependence between out-of-sample and in-sample. But the type of theory you have to prove is exactly the same at the expense of more notation. So we're simplifying our lives here a little bit. So the performance of the PCR is a random quantity. The benchmark is a constant. And what we care about is establishing a bound between the gap between these two quantities that holds with high probability. So let me say the same thing differently. We care about finding a bound BTP that holds with probability 1 minus delta t. And we want this bound to hold possibly for all t's. In practice, it's difficult to have a bound that holds for all t, but you can find a bound that holds for all sufficiently large t. If you can ask me what is the t0 after which this bound holds, so you can compute it. It's just extremely messy to compute it, so we haven't done it here. Okay, but if you cared about what is the t0 after which this inequality holds, you can do it. If you can establish an inequality that looks like this, that is such that the terms BTP and delta t go to 0 as t goes to infinity, then congrats, what you just established is an oracle inequality. And typically in learning theory, people care about establishing different type of inequalities that have different type of, you have pack bound, generalization error bounds, have all sorts of bounds out there. This is one of the bounds that you can establish. Typically, these bounds are not that different, if you ask me. It's just a matter of, they're very similar at the end of the day. And here we focus on oracle inequalities, which in my opinion are somehow the ones that, are kind of more common, I would say. I would like to make a few philosophical remarks about what this inequality means. Okay, as I said, in learning theory, people care a lot about this. This is not really how we typically establish consistency of our procedures, right? Typically, we like to show that parameters are consistent to the true value asymptotically, and they're asymptotically normal. In learning theory, in a way, the notion of large sample guarantee, it's a bit different. So let me try to emphasize a little bit what people care about in this literature. So first of all, we care about prediction accuracy. We don't care so much about estimation accuracy. So if the parameter is consistently estimated, good for you, but ultimately you care about forecasting performance. So having identification is something that, in a way, it's kind of less of a concern. If you care about forecasting, you should just kind of care about your loss. Second is that we don't care about achieving optimality relative to the truth, because typically we don't know what the truth is. We typically like to establish optimality relative to a benchmark. Often the benchmark is chosen as the best performing forecasting rule, across the forecasting rules that you have available. In this case, we chose the best linear forecast, which kind of makes sense. Third remark, we care about finite sample guarantees. We don't really care about asymptotic ones. And fourth point, and maybe this is the more interesting one, is that we care about the rate of convergence BT. Okay, so notice that BT is a function of the sample size T, is a function of this cross-sectional dimension P, and is a function of the principal components K. So in learning theory, people care a lot about how this term looks like, because especially in the analysis of large dimensional models, it is often the case that it's not clear at all how this term is going to look like. So if you have kind of a fixed dimensional parametric model, whether linear or nonlinear, typically these bounds would look like, these bounds in general would look like square root of log t over t. I'm saying in general because for the square laws you have better bounds, but in general they look like square root of log t over t. But if you have a large dimensional model, then this thing can be pretty wild. And so this term, typically, it's interesting because, this term tells you essentially, how much you can learn, what is the maximum sample size, what is the maximum growth rate for the number of parameters P that still gives you consistency, okay? And how fast am I going to reach the limit, okay? So we may agree or not if all of these things are interesting. I'll give you that and we can have a debate about it. But let me say that this is what the guys in learning theory literature kind of care about. And so in this strand of paper that I'm doing, I'm trying to whatever these guys are doing from the time series perspective. I didn't want to enter so much in whether this is the best performance measure or not. It has pros and cons, I would say. But this is what people in machine learning theory typically care about. Now, so important issue. It is typically the case that you can find a bound. Okay, so typically finding bounds for BTP, it's something that is, let's say, well, doable. It's not particularly complicated. Big issue is the bound that you find sharp? And that's a more complicated question. Okay, so understanding whether you have established a sharp bound on your performance measure, it's tricky. And surprisingly, as far as I know, there are very few optimal results. As far as I know, for principal component regression, we don't know what's the optimal result that you can get. I may be wrong, but I couldn't find it. So how can we understand whether our results are optimal or not? So in this paper, we're doing the following. So we're kind of taking the easy way around. So if you have a linear regression problem in large dimensions, so you just want to do linear regression with some predictors and the number of predictors is large, then Sibakov has established in 2003 that the optimal rate that you can achieve for essentially, so the optimal rate, the optimal learning rate for linear regression is k over t. Okay, so if I have if you have k parameters and you have t observation, you're doing linear regression, your risk cannot go to zero faster than k over t. So what we're interested in this analysis is the following. Can we recover this rate? So this would be the rate that you would achieve if the principal components were observed. So if the principal components that were observed, it makes sense to us to say that the optimal learning rate that you can achieve is the same that you would achieve if you just did linear regression on the principal components. Okay? So can we achieve this or not? Spoiler, so it turns out that in some cases you can achieve the optimal learning rate k over t. So in some sense, we know that in this context, PCR will be in some sense optimal. You cannot always recover it. Okay, so we do not know whether this means that the bound that we got is inefficient or that that's the best bound that you can achieve when under some scenarios of our general framework. So that we do not know, and this is a complicated question which we don't know if we're going to deal with. But as of now, what I can tell you is that, well, let me tell you exactly what happens. If you have pervasive factors, you can achieve the optimal learning rate, but when the factors are weak, then it looks like optimality is lost. So let me give you a sketch of the assumptions, and then let me show you the main result. So as I said, what we're trying to do in these strands of papers is to give you, in a way, kind of very standard results. So ideally, this could be results that you could have in a course because we're establishing properties of different forecasting procedure that we used in econometrics under fairly vanilla assumptions. So that's what we're really trying to do. So the assumptions that we have, I'll talk a little bit more in detail in a second, are really a union of the assumptions made by Fan and his co-authors in his papers about covariance estimation, In some sense, we have some of the assumptions we have are a little bit weaker than the assumptions of FAN, but by epsilon. So really, we're working standard assumption of FAN uses, which in turn are standard assumptions by Bayanang. So in a way, we're not having any real regularity conditions. We have a small ball assumption. So the small ball assumption is a powerful assumption, I would say, that is used to establish sharp bounds for learning theory. It was introduced by Mendelssohn, which is a very popular guy in machine learning mathematics. So that's an assumption is typically not used in factor models, but we shall require in some bits of the analysis I'm going to talk about. The only assumption that in a way is not standard, it's I would say, mild regularity condition on the density of the predictors. So in some sense, so we assume that the density of the predictors is bounded. But since the vector of predictors has a dimension that grows with the sample size, the way this assumption is formulated is a little bit ugly because the bound needs to vary with p. It's a bit restrictive to have a multivariate distribution that is bounded irrespective of the dimension. Okay. So this assumption is a little bit ugly. I'm terribly ashamed of this. I don't know why I talked about it. I should maybe skipped it. And we're working on kind of getting rid of it, but it's a little bit hard. I mean, you can't get rid of it at the expense of doing a much more complicated proof using chaining for mixing data that, to the best of my knowledge, no one has done yet, at least in the papers that we found. So with the exception of this last condition, for the most part, the assumptions are very standard. Let me give you a better detail of the assumptions. So we have assumption of the distribution. The data has some Gaussian tails. We have assumption of dependence. We're assuming a geometric alpha mixing. In particular, the coefficient R alpha is the rate of geometric decay of the alpha mixing coefficients. Eigenvalues, top k eigenvalues diverge at the rate p power alpha, where alpha is in between 1/2 and 1. We have an assumption the number of predictors. I'm not going to bore you with the mathematical equation, but essentially p can grow as a function of t, and p can be much larger than t. We also allow k to grow with the sample size, although the rate of growth of k, which empirically doesn't really matter because in practice we don't need k to grow with the sample size, but the theory allows for it, and it can grow, but it cannot grow by more than t power 1/3. So we can allow for moderately growing number of principal components. Then we have an assumption on the small ball, which I'll talk about, and then I have an assumption on the best linear predictor. So I'm not going to talk about all the assumptions because it's going to be boring, but I'm just going to give you more details about 3 things. So eigenvalues, this I'm not really going to spend much on it. So we assume that the largest eigenvalues of the population covariance matrix of the predictors diverge at rate p power alpha. Alpha can be 1. So that would be the strong signal case, analog of the strong factor model. Sorry, factor model with pervasive factors. And we also allow for alpha between 1/2 and 1. So weak factor model. I'm not going to talk too much about this. It's fairly straightforward. Now, second condition, it's kind of an identification condition. It's the so-called small ball assumption. This assumption is spelled here precisely how Mendelssohn spells it out in his papers on learning theory for IID data. So what this assumption spells out is essentially the same. It's essentially saying the following. If you look at the random variable that is defined as the difference between 2 forecasts, this random variable, in a way, cannot have excessive mass in a neighborhood of 0. So in a way, this is kind of an identification condition because it allows you to distinguish 2 different forecasting rules. And so you can say whether 2 different forecasting rules have different risk. Okay? And this assumption turns out to be very nice because if you have this assumption in place, there's a very cute proof strategy that has been invented by Mendelssohn, which allows you to obtain sharp bounds. I'm not going to have the time to talk about it, but if you have time to look at this paper by Mendelssohn, I would recommend you looking at it because it's kind of cute and it goes a long way for proving results for lasso, for linear regression, for random forests and things like that. As I said, let me emphasize that this assumption says nothing about the tails of the data, so it's not restricting fat tailness. I mean, we're assuming sub-Gaussian tails, so we're kind of restricted in that regards, but this assumption imposes no restriction on the tail. It's just kind of an assumption that if you have two random variables, sorry, if you have two different predictors, these two different predictors cannot be cannot be close to zero with too much probability. Otherwise, you will not be able to disentangle them empirically from the data. Okay, so we would say that it's a kind of a mild assumption. If you look at a lot of multivariate distributions, this multivariate distribution would satisfy this. For instance, random variables in the spherical family satisfy this automatically. So for spherical distributions, this will be true. However, of course, you can construct counterexamples in which this doesn't hold. So it's an assumption that in some setting is binding. I couldn't find an example that would convince me that this is a bad assumption, but people have worked on a couple of examples in which this doesn't hold. Now, the last assumption we have is the assumption on the best linear predictor. And again, let me introduce a trivial lemma to explain what we're doing with the next assumption. So, obvious lemma, if you have some vector of random variables, xt, you can always decompose this vector xt in the sum of two components, the principal components times some matrix of loadings, and ut, which I'm going to call the idiosyncratic component. And important, you can always do this decomposition in a way such that pt and ut, these two random vectors, are orthogonal. So this doesn't need to have any special structure in place. You just essentially just need the variance of x to be fine. Second important thing that I wanted to point out, again, trivial. If you're interested in the linear combination of xt with some vector theta star, so you can think of theta star as the vector of coefficients of the best linear predictor, but it could be any vector, then you can always do this straightforward decomposition. You can always decompose the best linear predictor in the sum of two components. The contribution of the principal components, and bar theta star here denotes the vector of coefficients associated with the principal components, and the contribution of the idiosyncratic term, okay, which is going to be ut times gamma star. And you can give closed form expressions to bar theta star and gamma star, and these are function of the vector theta star you care about, plus the eigenvectors and the matrix of eigenvalues associated with your problem. In particular, I would like to emphasize that essentially you can think of, gamma has a kind of an intuitive kind of expression in a way. So the contribution of the idiosyncratic vector to your forecast is essentially the linear combination of the idiosyncratic component times this vector, which is the projection of the vector theta star on the space spanned by the residual eigenvectors, okay? So the reason why I'm introducing this is because in the paper, we're making an assumption on this quantity, okay? So in a way, in a factor model, what typically people assume is that gamma star is zero, right? And so when you have this, you have that, if you want to forecast yt, you just need to estimate bar theta star. In this paper, we're allowing the idiosyncratic vector to have a contribution to the forecasting performance of your predictors. So you care about this term as well. But in some sense, we're assuming that the contribution of the idiosyncratic vector is negligible. So if you forecast only with the principal component regression, you don't care so much about this. So let me show you the assumption, and then let's make a comment. So we assume that there is some constant c theta star such that this condition holds. So if you compute the Euclidean norm of the gamma of the vector of contributions of the idiosyncratic component to your forecast, and you rescale this by p power alpha divided by 2, you have that this product, it's bounded by a constant, which does not depend on p. So essentially, this assumption implies that the components of gamma star need to shrink at some appropriate rate. So let me be very honest about this. So this, in a way, is 100% reverse engineering in the following sense. When assumption A6 holds, what happens is that the bias of principal component regression is going to be smaller than the estimation error. So asymptotically, you don't care about the bias because it's an order of magnitude, which is at most the same order of magnitude of your estimation error. Okay, so you do not need to assume a perfect factor structure to forecast well principal component regression. You can assume that there's some information in the idiosyncratic term, but this amount of information needs to somehow shrink a bit straight to still get consistency of PCR. Okay. Admittedly, this is a bit cheating, right? I'm reverse engineering the condition on the idiosyncratic contribution of my principal component regression representation to get the result I want. You can drop this. If you drop this assumption, I cannot bound anymore the regret of PCR with respect to the best linear predictor, but I can still give you the regret bound of PCR with respect to the best principal component regression that I can construct in population. Okay, so if you don't like this because it feels like cheating, I would tell you, I agree with you. You can drop it, and basically you're going to have a bound in which you need to change the quantity you compare your model against. Okay, so we thought that this was kind of nice because it kind of makes the point that you don't need a perfect factor structure to forecast well with PCR. But again, this is a little bit of a matter of taste. Cool. So main results. Assume that assumption A1 to A6 are satisfied, and then we obtain the following oracle inequality. So with high probability, we obtain that the performance of principal component regression is bounded by at most this quantity. Okay. I'm going to dissect a little bit this bound to give you some more insightful results because there's a lot of stuff going on here. So this is not really super informative at first sight. Let me, just to be clear, clarify that this bound under the assumption in the paper goes to 0 as t goes to infinity. So this is indeed an oracle inequality under the rate of growth on P on K that we are assuming in the paper. Okay. Now, this is great, but let me give you a better way of looking at this result. So let me introduce some extra bit of notation. So I'm going to use this symbol over here to say that with high probability, AT is smaller than BT times a constant that t goes to infinity. Okay, I'm just going to use this notation to simplify how I'm going to explain my inequality. So the result that I have implies that in the strong signal case, and if you assume independence between if you assume ID data, you recover this bound. So the performance of PCR is going to be at most 1 over P plus K over T times log T, the performance of the best linear prediction in the class. Clearly, this result implies that if P grows faster than T, then you recover the optimal learning rate K over T. So in some sense, principal component regression in a strong signal case is the optimal procedure that you may want to use for forecasting. Okay. Things get more sad in the weak factor case. In the weak factor case, if you assume against independence, you obtain this bound over here. Now, why this bound is a little bit more sad. So first of all, we still got K over T. Okay, great. This is the regret that you would have if you forecasted with a linear regression and you knew the principal components. Then, second term that you have is this term over here. It's P divided by T times P power alpha. Okay, so clearly, if alpha is equal to 1 in the strong signal case, right, this would be just 1 over T. So we will be pretty happy about that, right? Sorry, 1 over T squared. So this will go to 0 very fast. If you pick an alpha that is small, this term tells you that essentially you pay a price for the weak signals, and the price you pay is that in a way you need a larger sample size, so you need bigger T to achieve the same level of performance that you would have obtained if you had strong factors. So the price you pay for weak signals is that you need a larger cross-sectional size, a large time series dimension relative to the cross-sectional size to be able to learn accurately, to be able to forecast precisely, I should say here. And then, by the way, the condition P over T times P power alpha going to 0 is one of the conditions that Bai and Eng assume in a recent paper that they have about consistency of principal component regression. So, after we got the result, clearly thing that we ask ourselves, do the terms in our bound make sense? And, good news that yes, this term makes sense, because when this doesn't go to 0, Bai and Eng say that you don't have consistency of PCR for weak factors. Okay? And then the first term is also quite sad. It tells you that the learning rate that you have is going to be bounded by a function 1 over p power 2 alpha minus 1. So what this tells you is that when alpha is very close to 1/2, so let's say is 1/2 plus epsilon divided by 2, then this term is going to be 1 over p power epsilon. So clearly, if epsilon is small, this tells you that your regret bound is going to be very, very big, right? So essentially, this tells you that the weaker the signal, the slower you're going to converge to the asymptotic. Well, the slower your PCR is going to converge to the optimal performance that you can achieve asymptotically. So this is kind of bad news. Important thing I would like to emphasize, as you can see, in this bound, we get, so essentially this bound only makes sense, right, if alpha is larger than 1/2, right? If alpha is smaller than 1/2, this diverges, right? So it doesn't make sense. So in this inequality, we need to assume that alpha is larger than 1/2 to obtain consistency. Now, important thing that I would like to emphasize, and we're still kind of wrapping our heads around. So in the factor literature, it's known that consistency of the principal components requires alpha being positive. So as long as alpha is positive, you can consistently estimate PC, the principal components. So we also need to establish consistency of the principal components in our paper. So we have a consistency result. And in that consistency result, the rate requirement we have on alpha is alpha being positive. So, so what I'm trying to say here is that so our analysis seems to suggest that the condition alpha positive is sufficient for consistency of PCR, but it's not sufficient for consistency of the prediction risk out of sample. I'm saying suggest because maybe the reason why we got this is because our inequalities were not sharp enough. So we're trying to understand where we can improve this. Okay, but in all the intermediate results that are similar to results established in literature, we got the same conditions of alpha that our papers have established. Sadly, it looks from our analysis that these results are not enough when you look at the prediction risk to get a rate of 1 over p power alpha, which means that PCR is consistent for prediction when alpha is positive, and the best we could get is this one. Cool. So I have 10 minutes left. So I'm just going to talk very briefly about how the proof works, and then I'm just going to wrap up. So the proof is basically really a combination of arguments used to establish consistency in the factor model literature, together with an argument by Lecoux and Mendelssohn to establish consistency of a linear regression based on the small bound method. So just a bit of notation, I'm not going to talk too much about it, but there's just maybe one inequality that I just want to show. So we need to define a few matrices. So we have an approximate rotation matrix, which is the matrix H. This is the same matrix that it's used by Bai and Eng. We're using a bit of a different notation, but it's the same matrix used by Bai and Eng. And then we have two bar thetas, bar theta star and bar theta tilde. Bar theta star is the population principal component regression coefficient based on the true principal components. Okay, so this is just the the minimizer of the the L2 norm of this discrepancy. And then we have bar theta tilde, which is the sample least square estimator that is based on the true principal components. So if you observe the true principal components, which you do not, you could estimate var theta tilde. Sadly, we do not. And the best that we can do is having var theta hat, which is the estimator obtained by putting here on P a hat. Okay? So I'm introducing this notation because this will pop up in the next slide. So we have a basic decomposition that essentially is kind of the key of the proof. This does not require any particular assumption on the problem. You just need your data to be generated by some stationary process. And this decomposition doesn't really require any heavy maths. In the sense, it's just projection theorem, Cauchy-Schwarz triangular inequality, and CR inequality. But it took us a lot of time. So this, maybe you will be able to do it in a page. This took us, I think, 2.5 pages. And this is key because the problem that we had in writing this paper is that since we have a lot of estimation error to control, it's very easy to get a bound that is consistent for prediction, but is not sharp enough. So thanks to this inequality, actually, we kind of get a fairly sharp bound. So this was kind of very key to the proof. We haven't found similar results, so maybe this is nice. And essentially, what this inequality tells you is that it bounds the estimation error of principal component regression by a bunch of other estimation errors. So what you have here is that the approximation error of principal component regression, this is the estimation error that you would have. So, sorry, this difference over here is just the difference between the, let's say, population principal component regression coefficient and the sample principal component regression coefficient that you could compute if you observe the true principal components. Or this term is the difference between PCR computed from the population principal components versus PCR computed from the population principal components. So this error term is due to the error in computing the principal component regression. And then we have this term over here, which is, again, essentially an estimation error related to the problem of carrying out principal component estimation. Let me emphasize also that we believe this inequality is fairly sharp, and it was also nice about this inequality is that we get explicit constants. As you can see, the constants here are just 2, 4, and 2. Okay, so as you can see here, all the constants are very explicit. And essentially, the proof of the paper, which is long because with factor models, you have to, there's a lot of tedious work to do, but it's fairly straightforward. What the proof does essentially controls all of these terms. And, to make the long story short, the first two terms in this inequality are essentially controlled using arguments that are analog to the ones used in the factor model literature. So we do a non-parametric interpretation to PCR, but it turns out that a lot of the arguments that people make assuming a factor model go through, even if you don't really assume a factor model. And the third term in the inequality, it's controlled by using the small ball method. So this technique using in learning theory by Mendelssohn and co-authors. And then the last term is the approximation of PCR. And this is what is controlled by this is what is controlled using the assumption 6. But again, if you don't like it, you can remove it, and then you can control the regret you can control the regret of the principal component regression by simply comparing it against the population principal component regression you could do, which is unfeasible. And one remark that I would just like to say, and because I forgot to say, but I kind of care about emphasizing this, in the regret bound that we get, as you can see, it's not only a function of the strength of the signal, but it's also kind of a function of the degree of geometric alpha mixing of the alpha mixing coefficient, right? So this R alpha tells you how fast the alpha mixing coefficients go to 0. If R alpha is infinite, it means that it is IID. If R alpha is small, it means that the data is, well, geometric mixing, which means it's mixing pretty fast, but at a slower rate. Let me emphasize that we were not able, so this we would wanted to get rid of, we couldn't get rid of it. This term does not appear in other papers that deal with consistency of principal component regression. In particular, there's a recent paper by an Eng that does asymptotics for the weak factor model that does not have this term in a way, it only has this term. However, what a lot of these papers do is that they don't have this term because they essentially assume the rate of consistency of the sample covariance matrix for high dimensions. So we wanted to prove everything from scratch. I'm Italian, so we like things when are homemade. So we were not able to get rid of it, and we couldn't find papers that get rid of it once we do the proof from scratch. Presumably, this is something that you could get rid of. Admittedly, a lot of people believe that you can get rid of this. But the shortcut that few papers do is that they just assume that the sample covariance matrix is consistent at the rate P over T. And so if you assume that directly without proving it, then you don't have this term, okay? So if you're willing to make this additional assumption that Bai and Eng are making, then, well, this term would disappear from the bound. We didn't want to have it, so that's why we paid this price, and which is a little bit of a, a little thing that we don't really like in the bound, but we can really get rid of it. So let me wrap up and just say, so this is a fairly straightforward paper. We analyzed the prediction performance of empirical risk minimization for principal component regression. We established oracle inequalities for both strong and weak signal regimes. And in a way, highlight of the analysis is that we're trying to be as non-parametric as possible by not assuming that the data is generated by a factor model. And what is kind of nice is that if you like factor models, because that's there's a lot of support in economics, both in theoretical and empirical for factor models. So if you like to assume them, that's fine. But actually, you don't have to. And a lot of the results that people have established under the factor model assumption cannot carry out in a more general setting in some sense. And with it, I'll leave it here. And I don't want to brag, but I've been perfectly punctual. So yeah, that's it. Thank you so much.
Fantastic. Thanks so much, Christian. I will stop the recording and I